So, welcome to the material lecture of the material science. As usual, let's recall what we have learned in the last lecture. Last lecture, we start to work on the crystal systems and Bravais lattice. I hope you still remember. And we are going to talk about this in the next page. But before that, I want you to know the crystal structure of the metals. There are four basic structures we learned last week, the previous lecture. They are simple cubic structure, right? Face center cubic structure, body center cubic structure, and the hexagonal closed pack structures. How you remember? Anybody want to tell me what is this structure? Anybody want to tell me? 0.5 points. Early bird. Early bird. Anybody want to tell me which one is this? Yes, please. Body center cubic. Thank you. Body center cubic, right? You have a one ball or you have one element in the center. So this is called body center, right? Good, very good. Thank you. Okay, so in order to understand some information about this crystal structure, we have to identify a unique cell. So what is a unique cell? This is called unique cell, right? The definition of unique cell is that the smallest repeated unit, right? So there are two informations. The first information is smallest, right? The second is repeated in all directions, right? X-axis, Y-axis, and Z-axis. Okay, so this is important. So this is called unique cell. And this one, the first information we need to know is called coordination number. Right? So what is coordination number? Okay. What's the coordination number of this unique cell? Anybody want to tell me? Raise your hand, 0.5 points. What's the coordination number in this case? How many? Answer me, 0.5, early birds. Yes, please. 8, right? Thank you very much. Very good. 8. What's coordination number? 1, 2, 3, 4, 5, 6, 7. 8. The one behind this atom, right? So there are 8. The coordination number is 8. What does that mean, coordination number? The one who is the close pack for this sphere in the center. So the sphere touched the sphere in the center. This is this is the one, right? So we have 8 atoms, which is close touched with the spheres in the center. Okay, and then second information is how many atoms in this unique cell. Again, I think I figure out one very important points for the early birds. This is the time you can get points instead of call the roll, right? Okay, so I want to give you points as much as I can in order to tell people you should come earlier. Okay, so what's the how many atoms per unit cell in this case? Anybody want to tell me? Yeah, thank you. That's 2, right? 2. Okay, 0.5. Yes. So how many? Why this is 2? Because there's one whole atoms in the center. That's 1, right? And you have 1/8 of the atoms in the 8 corners. So you have 1/8 of the atom, and then there are 8 corners. So 1/8 times 8 equal to 1, right? So that will be 2. Okay, so thank you. That's very good. And then after that, you need to know the cubic edge length related to the atomic radius. So this is called cubic edge length, right? Cubic edge length. And then this is radius. So you need to know the relationship between the atomic radius and the cubic edge length. Okay? And then after that, when you know this all the 3 information, and now you need to find out what is atomic packing factor. This is the equation for you to understand the atomic packing factor, which is the value of the sphere divided by value of the cube. So you know that this is kind of ratio. This is a kind of dimensionless quantity. Dimensionless quantity tell you that how many empty space in this unit cell, or how many, what's the how many space occupied by the sphere in this unit cell, right? Okay, and so this is equation. And now the final information you want to digest is the theoretical density. The theoretical density represented like this. Okay, so ladies and gentlemen, I want you to remember these two equations. And this will show up in your final exam. And you have to do some basic, simple calculation. Okay, this is no problem for you at all. But before you do the calculation, you need to remember these two equations. Okay, and then finally, we talk about polymorphism, or the same word, the same meaning of the polymorphism is called allotropy. Okay, that means what? That means that one type of the atom, one type of the structure can be changed to another type because you change the temperature. This is one of the case. For example, we give you an example in the previous lecture is that when you have a tin metal, and the tin metal at temperature above 13.2 Celsius, the tin represent like this. However, if you drop the temperature below 13.2 Celsius, then the structure of the tin looks like this. I hope you remember I showed you a video, right? A video precisely showing you that the temperature change, the structure change. So the tin bricks collapsed, right? Have you seen a tin brick, right? And then you drop the temperature and bricks collapsed. Okay, that's the example. Another thing is that, you know, the carbon at the room temperature has two forms. Well, so far there are 4, 5, 6 forms. And in this case, in the previous lecture, I showed you two forms, right? The one is called diamond. One is called, what's that? Graphite, right? Graphite. Graphite is sp3 hybridization structure. And then diamond is sp3, right? Graphite is sp2. Okay, and then last week, previous lecture, the most important information you need to know is called crystal structure. I hope you still remember, and this need to be, this is very important. So crystal structure equal to what? Crystal structure equal to crystal lattice plus basis. So you have 14 crystal lattices. Remember this? You have 14 crystal lattices. And then first information is crystal classes. There are 7 crystal classes. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. So this triclinic, right? This monoclinic. This is monoclinic, right? And this is tetragonal. So there are 7 crystal classes, and there are 4 types of lattice type. What's that? What does that mean? Lattice. Lattice means that you have this structure, and then it depends on where you want to locate the element, or where do you want to locate the atoms. For example, simple cubic structure is you locate the atoms in the 8 corners, right? And value center means, or you can call this body center. You put atoms in the 8 corners as well as in the atom in the center, right? And this is base center. Base center means you put these atoms in the only 2 faces. One is on the top, one is in the bottom. And face center, you put the atoms not only in the 8 corners, but in the 6 faces, right? So this is called face center. And you have 8. You have this. You you put the atoms in the position in this cubic cell. So this is called crystal lattice. Okay, there are 4 crystal lattice. So this is only 14, right? There's nothing more than this. So you cannot, if you find, as I hope you remember, if you find number 15, and that would be a good chance to let us to get Nobel Prize, right? Okay, so if you find the number 15 crystal lattice, and we can work together. Right, so first information we want to know is called crystal lattice. And the second one is basis. What is basis? As we know that if you put the atom in this A corner, if you put 8 atoms in the A corner, can you put molecular in the A corners? Yes, you can. Okay, you also can you also can put a ion pair in the A corners. And also you can pick up 8 atom pairs to put in these A corners. So this is called basis. So basis can be atom, 1 atom, can be 1 molecules, which can be 2 atoms, 4 atoms. Okay, and it also can be ion pair like sodium chloride, or you can put a atom pairs like what? Like a carbon, right? Like a diamond, right? With the angle of what? 109 degree. Okay, so this is called basis. And you know, this is a Nobel Prize winner. He found out another crystal structure called quasi-crystal, but it doesn't belong to these 14 crystal Barbius lattice. So, but anyway, he got Nobel Prize. Okay, so this is the information you need to know, and that's it for last lecture. So today we are going to move to a new topic, which is we want to address points, vector, and a plan in a unit cell. So then we move to the second important topic, crystallographic point, direction, and plans. Let me figure out whether I have recorded this. Okay. So now let's start to think in this cubic unit, or in this cubic cell. In this unit cell, I should say, not cubic, unit cell. If you have a point in this unit cell, or if you have a direction we call vector, you know, in this unit cell, or if you have a plan in this unit cell, how are you going to address them? Can you address them precisely, scientifically? Scientifically means that once you say something, everybody knows. You know, if you don't say anything precisely, you cannot communicate with another scientist or engineers. So let's start to define what is this. The basis for determining index value is the unit cell with a right-handed coordinate systems consisting of 3 axes situated at one of the corners and coinciding with the unit cell edges. Okay, so what is this? Let's start with in the section 3.8, point coordinates. So you have a point in this unit cell. For example, the point P in a unit cell here. So how are you going to address this precisely? Okay, so I hope you remember we have x-axis, y-axis, and z-axis. And you have a kind of angle here, right? Alpha, beta, gamma. So when you have a point here, you project this point to the a-axis, with a fraction of this a. So this is the h length, right? So this length is a fraction of the h length. So q is the fractal length of the a along the axis. So this is called qa. And r, you have r here. R is the fraction length of the b along the y-axis. This is called RB. And for S, here is the fraction length of the C along the Z-axis. So this is called SC. So as a result, wow, easy, right? You can say QA, RB, and SC. And if you write down these three numbers, people will very soon pick up what do you want to talk. So this is called point coordinate. I don't think this is a problem. Easy. Start from x-axis, and then y-axis, and then z-axis. So we have some examples. Bless you. Okay. So examples problem 3.4 to 3.5. We skip, too easy. So section 3.9, crystallographic directions. And we divide this topic into two parts. The first part is called cubic crystal. The second part is hexagonal crystal. So let's start from the simplest example. So crystallographic directions is that crystallographic direction is defined as a line between 2 points or a vector. So you need to draw a line, something like this. And I'm sure you understand because this is a cube. So you have the h length in the x-axis, y-axis, and z-axis are all equal. Okay, ladies and gentlemen, I want you to remember these 4 steps very well. And I want you to, this will be in your final exam, but I don't want you to remember, but I want you to remember the concepts of these 4 steps. So in your final exam, that will be easy for you to get the right answer. Okay, so 4 steps determine the 3 directions. Okay, the first one, the vector passes through the origin. It has to be from the origin. Okay, of the coordinate systems, any vectors may be translated throughout the crystal lattice without alternation if parallel is maintained. Parallelism, right? Okay, the second point is the length of the vector projection on each of the 3 axes is determined. These are measured in terms of the unique cell dimensions, which are A, B, and C. The third step is these 3 numbers are multiplied or divided by a common factors to reduce them to the smallest integer values. Okay? The step 4 is the least 3 indexes not separated by commas are enclosed in a square brackets. So we have square bracket and we use UVW square bracket to represent this direction. So the UVW integers corresponds to the reduced projection along the X, Y, Z axis respectively. Are you clear with these 4 steps? No, you don't, right? No, you don't. Anyway, let's do the real practice. So then you will understand better. Okay, so now let's have a one vector here. And we follow the 4 steps we just talked about. So determine the index for the directions showing in the accompanying figures. This is the direction. So in your final exam, I might give you this example. I want to give you this vector in the Unix cell, and I want you to tell me what's the index. What are these three numbers I just told you in the previous slide? Okay, or I give you last three numbers. I want you to draw the vectors in a Unix cell. Okay, let's practice right now. So first step, the vector need to pass through the origin. Need to start, this vector need to start from the origin, which is here, because this x, y, z axis, right? Okay, so it need to pass through the origin. Does this vector pass through this origin? Yes, it is, right? Step 1. Step 2, this vector need to do the projection to the x-axis, y-axis, and z-axis. Step 2. So while this vector project to the x-axis, this will be the length of this vector in x-axis. Easy, right? In this case, it's half of A. Half of A. Okay, and in the x-axis, and then this vector project to the y-axis, which is what? 1, right? Which is 1 of y, or 1 of b, 1b, right? And so this is b. And then this vector project to the z. What's the z? Z is here. So that will be 0c. So as a result, you can get this. The step 2 is three numbers, half a, 1b, and 0c. Okay? And then step 3. What is step 3? Take this out. Become a unit parameter. You take the a, b, c out because of what? Because this is a cubic structure. Cubic structure, x equal the length of the x in the x-axis and length in the y-axis and length in the z-axis are all equal. So you take a, b, c out. And then, you know, the step 4, you need, sorry, this should be step 3. Step 3. Step 3 is you need to make it become the smallest integers. Why? This is not an integer, right? So you need to multiply 2 in these three numbers, for these three numbers. So that will be what? 2. That will be 1, 2, and 0. And you use square bracket to block these three numbers. 1, 0, 2. 1, 2, 0. Are you with me so far? Yes, right? Piece of cake. Top 15% students in the country. Okay. Right. 1, 2, square bracket 1, 2, 0. So in your midterm, in your final exam, if I give you this number, I want you to draw this vector for me. Or if I give you this vector in a cubic cell, I want you to tell me these three numbers. No problem, right? Okay, let's practice more, and then I think you will catch my point. So, three information. Step 1, origin. The keyword is origin. Step 2, the keyword is projection. The step 3, keyword is reduction, which make it become the smallest integer, right? The step 4, keyword is enclosure. You use square bracket to put these three numbers together. No problem, right? Piece of cake. Okay, let's practice more. UVW. We use UVW to represent these three numbers. First one, 100. Anybody want to tell me where is this 100? If I give you three numbers, 100. So 100 means what? If you do the smallest projection, this is 1. So it should be here, right? You draw a vector for me. This 1 is here, right? So the projection 1 is here. And projection 0 is what? Is here for y-axis. Projection 0 is in z-axis is here. So the vector will be this one. This is called 1, 0, 0. No problem, right? Okay. Next one. 1, 1, 0. Easy, right? 1, projection in x-axis 1 here. And then projection in y-axis is 1 here. Projection in z-axis is 0 is here. So if you combine these two vectors together, that will be what? That will be this one. Square bracket 1, 1, 0. This vector represent 1, 1, 0. Okay. Next. 1, 1, 1. Easy. Please do this for me. No problem. Okay. So how about this? Tell me what is this? Square bracket 1 and 1 over bar and 0. What is this? What is over bar? This is negative. It represent negative. You know, 1 is positive, right? And then 0, minus, it should be minus, not positive, minus. Okay, so this vector means what? Over bar means the minus. This is positive, this is plus, this is minus. So the direction go to this way. Okay, so when you see something, when you see a number with over bar on the top, and then you know that this is the minus direction, or you can say the negative direction. Okay. So here, let's see what's the square bracket 1 over bar and 0 square bracket. Draw a direction of this in a cubic unit cell. So first one is here, and then 1 over bar, this is 1 here, right? 1 over bar is here, and then 0 is here. So can you draw this for me? Projection this and get P points. So this is the direction of the 1 over bar 0. Easy. Okay, so I just told you the 4 steps. Please remember this well. Remember the keyword very well. Origin, projection, smallest integer, and then square bracket. Please tell me, what is this? Projection, right? Projection 1, projection 0, projection half of z, right? So it's 1, 0, 0.5 or half of z. Okay, okay, half, and then that will be 2. You know, you need to make this become small integer. So 2, 0, 1, and then square bracket. Okay. How about this vector? This vector is what? Projection to the x-axis, y-axis, and z-axis. To the x-axis is minus, right? This is positive, and this is minus or negative, minus. Right, and then projection to z. So minus 1, and then what? 1 to z, and 1 to z. So minus 1, 1, 1. And this already is the smallest integer here, volume here, and then we just do this. Well, where over bar represents a negative index. Easy. Okay, so we have a term called families of the direction. The family of direction, we are going to talk about this very soon. So let's skip this at this moment. So the first information you need to know is the crystal structure of a cubic structure. And then how about hexagonal? there are 4 axes for the hexagonal crystals. So this is A1, there are 4. They are A1, A2, A3, and Z. So there are 4 axes for this case. So A1, A2, A3 axes within a single plane. Oh, here we call basal plane. Basal plane is this one. This is called basal plane. And then this A1, A2, A3 has the angle between these 3 axes are 120. So as you know that if you 120 times 3, that will be 360. No problem. So Z axis is perpendicular to the basal plane. Okay, so this is Z axis. Okay. Right. So 4 axes are also called Miller-Blavius. Don't worry about this. But I want you to know how to represent a vector in the hexagonal crystal. So directional indexes are denoted by 4 indexes as UVTW for A1 axis, A2 axis, A3 axis, and Z axis. So hexagonal closed-packed crystallographic direction, again, you follow these 4 steps with 4 keywords. Okay, again, origin, projection, smallest integer, and then square brackets. Okay, let's take a look at the first one, this one. The square bracket 1, 1, 2 over bar 0. So this is the one. Why this can be determined like this? If I give you a direction this way, can you tell me this answer? Can you? Okay, let's find out how they do that. So let's take a look of the basal plane first. Basal plane of the this is the direction here, right? So if you do the projection of in the A1 axis, that will be half of A. If you do the projection of the A2 axis, that will be again is half of B. Half of A2. So if you do the projection of the Z, that will be what? That will be minus 1, right? Because this is the plus direction. This is minus direction. So that will be what? That will be half of A, half of B, and minus 3A. Half of the A1, half of the A2, and then 1 A3. And how about Z-axis? That will be 0, right? So when you something write down like this, half of A1, half of A2, and then minus A3 and 0. So you do the smallest integer value. That will be 1, 1, minus 2, and 0. And minus 2 means what? 2 over bar. So the answer is square bracket 1, 1, 2 over bar 0. Again, if I give you this number, please tell me this direction. Or I give you this direction, please tell me these numbers in your final exam. Okay? Right, let's practice more. 0, 0, 0, 1. Square bracket 0, 0, 0, 1. Why is this? This is because it's all in the A1, A2, A3 is all 0, right? So it's here. And 1 is what? This is the direction. How about 1 over bar 0, 0? 1 over bar 1, right? Is here. 1 is, and 1 over bar is here, right? It's here. This 1 is 1 over bar, right? And then 0, 0. This is 0. This is 0. That means what? If you combine these two vectors together, that will be this one. No problem. How about 1, 1 minus 2 over bar 0? I think we just practice this, right? So this is the one. Okay. Right. So there's a. I wonder whether you will be wonder about one thing. I hope you still remember when I talk about close pack sequences of the FCC. That will be A layer, B layer, C layer, A layer, B layer, C layer. That's what we call ABC packing sequences, right? So when we talk about hexagonal close pack, that will be A layer, B layer, A layer, B layer. So it's AB packing sequences. But when we think of these two structures, they all represent almost the same thing because the A there, B there, C there, they also has the same atoms. So in this case, the APF atomic packing factor are all 0.74. Hope you still remember. So that means what? That means we can convert this 3-index system into this 4-index system because they are all the same for the FCC and hexagonal closed pack structure. So that means what? That means we can convert the vector to represent in the cubic structure to the hexagonal structure. Okay? So in order to convert from 3-index system to the 4-index system, we can follow this equation. So this UVTW represent the vectors in the hexagonal closed pack, right? And then U prime, V prime, W prime represent in this cubic structure. For example, this one here, and this vector can put it in here, and you can do the same. You can represent the same thing. So we have a conversion equation like this. But I don't want you to remember this equation because you can find out it's easy and you can do a very easy calculation. Here, I just give you an example. Square bracket 0, 1, 0, and I want you to change it into hexagonal crystal structure. So that will be, if you do the simple calculation, you'll find out the answer easily. Okay? So from 0, square bracket 0, 1, 0, it can be square bracket 1 over bar 2, 1 over bar 0 after you do the calculation. Please do this by yourself. I don't want to waste your time here. Okay, easy. But be honest, you don't need to remember this because, again, you can easily to find out this when you want to do the calculation. Right, so next very important knowledge you want to know is we call a family of the directions. What does that mean, a family of the direction? You know, when we talk about in a cubic crystal directions for all the edges, when we say 1, 0, 0, 1, 0, 0 is this one, right? 1, 0, 0. How about 0, 1, 0? 0, 1, 0 is this one, right? Okay, how about 0, 0, 1? 1, 0, 0, 0, 1, 0, and 0, 0, 1. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Are these three represent the same thing or not? For the cubic crystal, if you put the atoms in, for example, this is body center cubic. If you put the atom here and you address the vector here 1, 0, 0, and 0, 1, 0, and 0, 0, 1, are they represent the same thing? Yes, right? So they are the family members in this group. They are family members in this group. Why? Because in the universe, there's no ready origin. You can point origin here. You can point origin here. You can point the origin here too. Right? So they are represent the same. So these three are the same members in this family. So how many family members in this case? How many family members? I told you one here, right? One here. One here. There's three. How many of them? There are 6. So one here, another one is what? This one. Another one is what? This one. Another one is what? This one. So there are 6 members in this family. And how are we going to represent this family? We use carat brackets. This is called carat bracket. 100 carat bracket. Okay, so when I write down this square carat bracket 100 square carat bracket, it represents 6 members. They are 100, 1 over bar 00, 010, 1 over bar 0, 001, 001 over bar. Okay, so this is for the cubic crystal. How about tetragonal crystal? Tetragonal crystal looks like this. So if I write 100, 100 here, how many members in this family? How many? 4, right? Why? Because in z-axis, this is called tetragonal symmetry. This is not a member of this in this family. Are you with me so far? Yes, right? So there are 4 members in the family. Okay? They are this one, this one, this one, and this one. Okay? So let me give you some tests, a family of directions. Now we only talk about cubic crystals. So 001 carat brackets 001, there are 6. I just told you, right? This one, this one, this one, this one, this one, this one. There are 6. So there are 6. How about this? 1. How about 011? Or you can write down carat bracket 110 or 011 or 101. Normally you write 110 or 011. How many members in the family? What's 011? So 011 is what? Sorry, 011. What is 011? It's this one, right? Sorry, 011, not this one. 011 is this one. Will this belong to the family of 011? Yes, it is. Right? So how many members in the family? There are 12. Can you find out for me? Can you? Yes, right? Because if you think about the plan, this is what? 110. So that means what? X is 110 here. So in one plan, there are 4 members in the family. 1, 2, 3, 4. This is one plan. So there are 3 plans. Right? There are 3 plans. So you have 4 times 3, that will be 12. So there are 12 families. 12 members in this family. Okay? Use your imagination to think. Should be no problem, right? How about 111? How many members in the family? 111 means what? 111 means this direction. 111. How many members? 8 members. Why? You know, you go this is 111. And there are 8 directions. Right? You have positive, positive. You have positive, negative, positive, negative, positive, negative. Right? So there are 8 members. Use your imagination. If you don't understand, please come to me after the class. We can discuss this more. Right. So This is one of the important knowledge you need to know, which is how to address directions in the Unix cell. And next one is how to address a plan or plans in the Unix cell. The topic is crystallographic plans. And then there are 5 informations you need to know here. Again, the first one is how do you use numbers to address this plan. We call Miller indexes. The second one, again, we want to learn about the family of the plan, like the family of the direction, the same. The third one is, again, the hexagonal crystal. You need to convert the hexagonal crystal structures and the plan in the hexagonal crystal structure to the cubic structure, or from the cubic structure to the hexagonal crystal. And then the topic 4 and 5 are atomic arrangements and the interplanar spacing. But I don't think I have time to talk about this today. Okay. So the crystallographic plan, this is a Unix cell, right? If I draw a plan in this Unix cell, I want you to tell me, and I want you to communicate with your friend about this plan. Can you use 3 integer numbers to tell him, and then he can easily to understand? That's the point here. Again, if you have a vector, I want you to use 3 numbers to represent this vector, and your friend or your classmate will immediately understand. That's the way of the scientist, right? Okay, so again, the Unix cell is the basis, and the crystallographic plans are specified by 3 Miller indexes, as we use parentheses HKL. So the parenthesis is the one you represent. If you use square bracket, that means what? If you use square bracket, that means direction. And if you use parentheses, and that means plans. Okay? So the Miller indexes is what? A set of the 3 integers, again, or 4 for hexagonal crystal structure, that designate crystallographic plans as determined from the, again, reciprocal of fractional axis intercepts. Okay, you might don't understand at this moment, but let me tell you, there are 5 steps to determine the Miller indexes. You know, in order to get the point of the direction or vector, there are 4 steps you need to follow. But for the plan, Miller indexes, you need 5 steps to determine the Miller indexes. First one, there are 5 rules for the procedure. The first one, again, origin. Okay, but the plan shouldn't pass origin. It cannot. If the plan pass origin, you need to move parallelly. Anyway, I'll give you examples very soon. First step, origin. Second step, the length. Intercept. There's no projection at this moment. You don't need to do projection. So the intercepts, the length of the intercepts. Second one, a third step, reciprocal. For example, if this plan pass x-axis is 1, what's the reciprocal of 1? 1, right? Okay, then if this plan doesn't touch z-axis, that means what? The number will be 0, because if it touch x-axis, that will be 1. If there's no touch, like this plan, there's no touch of z-axis in the z-axis, that will be 0. So what's the reciprocal of the 0? It's infinite. Sorry. No, sorry, I'm sorry, I say it wrong. When this plane doesn't touch this plane, that means what's that? Infinite, never touch, right? And then, so we use this infinite. So the reciprocal of infinite will be 0. Okay. Right. So the number 5 is step 5 and step 4. Step 4 is the smallest integer. Again, when you get 3 numbers, you need to make it as you need to make it to become 3 integer. And then you use parentheses to mark to blank these 3 numbers. Okay. So let's start to make this as an example. Can you tell me this example? Yeah. 1, right? Origin. It doesn't touch origin, so this plan can be used to repeat. This plan can be used using middle indexes. There's no origin here, and you touch 1 here, right? And then 1 here, and then infinite, because this plan doesn't touch z-axis. So that will be 1, 1, infinite. So 1, 1, 1, infinite. Reciprocal, that means what? 1, 1, 0. So 1, 1, 0, and you need to make it become smallest integer. Again, its smallest integer is 1, 1, 0. Okay, and then you need to use parentheses for these 3 numbers. So the parentheses 1, 1, 0 is this plan. So if I give you parentheses 1, 1, 0, can you draw this plan for me? Yes, you can, right? How about this one? Let's practice together. So this plan is here, this plan here. So this is half of A, right? This is half of A. You might say, well, Professor, how do I know this is half? Wow, use your imagination. This is in the middle, right, of this line. It can be half. Half of A, and this is 1 of B, right? 1B. And this is, again, this is infinite. So for the intercepts, first of all, origin, important, origin. Second one, intercept, half of A, 1, B, and infinite C. Of course, you take A, B, C parameter away. So that will be half, 1, infinite. And next step, reciprocals. Reciprocals means what? 2, 1, infinite. And you want to do the smallest, you want to make it become smallest integer, so you do the reduction. Is this the smaller integer? Yes, it is. So it's 2, 1, 0. And you do the enclosure. That means you use parentheses for this. So use parentheses 2, 1, 0. So these 3 numbers represent this plan. Okay? Again, if I give you this plan, you need to tell me this. You need to tell me the middle indexes. If I give you middle index, you need to draw this plan for me in your final exam. Okay? You might say, wow, Professor, why we need to learn this? Is this important? Yes, this is very important. And this is very important to tell you something. Okay? So this is very important information. So please learn this, and we are going to talk about this application for you in the future. So why do I learn this? For you to use in the future. Right, let's take a look of the example 3.8 plans. Okay, I give you this plan, and I want you to tell me the parentheses HKL. Can you tell me this? First, step 1, origin. Does it touch the origin? Yes. What's going on? What should I do? Move the origin, or move the plan parallelly to x direction, y direction, or z direction is up to you. Okay, in this case, in the textbook, tell us that this origin moved to the right-hand side. We call O prime. So in this case, we can tell you the Miller indexes because we passed the first step. Second step is what? Intercepts. So what's the intercepts? For the x-axis, that'll be 1, right? For the y-axis, that'll be what? That'll be what? -1. Sorry. For the x-axis, it doesn't touch, right? Okay. For the y-axis, that will be 1. For the z-axis, that will be half of c. That will be half. So the answer, so you do the intercepts is infinite, -1, and then half of c. So you take ABC away, so that will be infinite, -1 and half. And next step, reciprocal, infinite will be 0. Infinite of -1 will be -1. Infinite, reciprocal of the half will be 2. So you do the reduction to make it become smallest integer. So that'll be 0. It's not necessary, right? So you do the parenthesis enclosure. That'll be parenthesis 0, -1, 2. So 0, 1 over bar, 2. And then in this case, again, you might raise a question, say, Professor, can I move this origin to the left-hand side instead of right-hand side? Or, Professor, can I move this origin to the top, to the upper, or down to this cubic cell, unit cell? And well, I got a different answer or not. Okay, so let's find out. So this is the original plan, and then this plan has a close to the origin, and then this is the case we just told you, right? The origin moved to the right-hand side, and of course the answer we got, we already know. The answer we got is 0, 1 over bar, and 2. That's what we talked in the previous slide, right? Okay. How about if I move the origin to the left-hand side? Can I get the same answer of 0, 1 over bar, and 2? Can I? Let's find out. So this O double prime, and then of course we need to extend this plan because this needs to be touched to x-axis, y-axis, and z-axis, right? So we put this and we extend this plan here. Can we? Yes, we can. Okay, so how about x-axis? Again, it's infinite, right? Because it doesn't touch x-axis. How about y-axis? It's here, right? How about z-axis? It's here. So that will be what? X, Y, Z will be infinite and 1 here, right? Because this is the plan. 1 here, and then half of Z. So half minus half. Okay? And then you do a reciprocal. So that'll be 0, 1, and -2. And then if you do the parenthesis, will be parenthesis 0, 1, 2 over bar. Did you get the same answer? No, you don't. But does this 2 tell you the same thing? Yes, it is. Why? Because these 2 belong to the family. They are a member of the family. Okay? Remember I told you the member of the family? in the direction. Again, the plant also have a family. So this is the member of the family. Okay? Right, so let's try more. So let's move the origin to the front. We call this O triple prong. This doesn't work. Why? Because no matter you move the origin to the front or to the back, this plant will always touch the origin. So this one doesn't work. So forget about this case. Okay? So you put the origin to the left, to the right, to the front, to the back, and now you put on the top or to put into the bottom. This is Z direction. Can you? Yeah. You put, this is called tetraplan. Tetraplan. And then again, you need to do this X tetraplan, Y tetraplan, and Z tetraplan. So this plan needs to touch this origin, these three axes. So let's do it. No, it doesn't touch, right? It doesn't touch this one more time. So in this case, again, this is what? Infinite. This is what? -2. This is what? 1. So infinite, -2, 1. Reciprocal, right? Can we do reciprocal? 0 minus half, 1. Smallest integer. Reduction, 0 minus 1, 2. This is the answer. Parenthesis 1 over bar 2. Take a look at this. The same. Okay. So no matter you move the origin to the in the x-axis or y-axis or z-axis, it always tell you the same answer. So you don't need to worry about this. Well, you might say, well, there are many cases. No, yeah, it's only one truth. That's the member of the family. Okay, so this tells you the information I want you to notice. You know, you can parallelly move to this plan. In another word, you know, instead of parallelly move to this plan, you can move the origin. It means the same thing, okay? Right, so let's do more practice. Meter index 100. Where is this? Can you tell me the plan? Yes, you can. Easy. Right? This is 1. How about 210? 210. Move it reciprocal. Half A 1 B infinite C, and that will be what? Half 1 infinite. That will be this one. Okay. And then graphic plans 2 over bar 1. Again, reciprocal. Right? Reciprocal. Half A, half B, half A, half B, and then -1. That will be this one. Okay. So this is 0 minus 1, 0, 1 over bar 1, parenthesis. Okay, please do this, practice this by yourself. I think this is easy. So again, this is easy. I think I want to skip this. This plan, please tell me, do this practice by yourself. This one again. If you don't understand, come to me after the class, okay? Do this by yourself. How about this one? If I show up this one to you in your final exam, Please, you know, this is about half. This is about what? 2/3 or 3/4. That will be okay. If you regard it as 3/4, that's okay. Or 2/3, that's also okay. But you know, it's about 2/3, right? It's not 3/4, right? Okay, intercepts. Okay. Oh no, I'm wrong. 3/4. What the? Okay. Anyway, I might have a ruler. I might mark here for you. Just don't let you mix up with this. Okay, so the answer is what? 634. Please practice this by yourself. It's hard for me to believe this is 3/4, right? It looks like 2/3. Okay, Miller index, parenthesis 634. Right, again, this is the family. The family of the plant. This is the family. This is the family. This is the family. And how do we represent the families? Before we use Cara blanket. Cara blanket to tell you that the direction. How about the family of plant? We use brass blankets. This one, brass blanket. Okay. How about brass blanket 100? How many faces? How many members in the family? All the faces. This is 100, right? 100. So there are 6 faces. That means there are 6 members in the family. How about 111? 111 means what? Means this one. I mean, in this case, it's all we are talking about. This one, in this case, is all cubic structure. Okay. So 111, how many members in the family? 8. 8. Okay. There are 8 members in the family. Okay, so 111, 100. I just talked about this. 1, 2, 3. Okay, please try to practice by yourself. And the important thing for this is that, you know, when you have the very interesting thing is square blanket. This direction is all perpendicular to the plant. So if you use 100 direction, that will be always perpendicular to the 100 plant. So in this case, this is 010 direction, and this is the 010 plant. It's always perpendicular. So this is the case of, you know, the 020 is the same. About 111 direction will be perpendicular to what? 111 plant. Always. So you need to remember this. That's the beauty of this index. The beauty of this index. Thanks for scientists and engineers. They create this kind of numbers for us, and it's very beautiful, right? Right. I think we run out of our time. Hexagonal crystal. I think I will leave this for the next week.